yesterday. So I'm not going to repeat size. It's going to be mostly composition, shape, internal structure, and packing. And when I mean packing is aggregation. There's packaging, which is what's happening in a particle, and by packing I mean when particles stick to each other and become this porous material. To be able to use optical measurement to study oceanic particle or lake particle, whichever you're interested in aquatic medium, we need to develop an understanding of how light interacts with matter. This is also true for the atmosphere. But the reverse side is if light was not if optical properties of particle did not vary for different particles, we could not use optics to differentiate between them. So we're not using acoustics to study phytoplankton because it's not going to interact well with them in a way that we can get a signal out that's useful for us. It's not that acoustic is not good, it's just not good to differentiate those particles. So we're using optics, or we're using it because it is dependent on what we have in water. So the basic problem that me solved had to do, you have a plane parallel light interacting with some sort of particle that's embedded in a medium. The medium can be air, it can be water, it can be anything you want. And how will this affect the light that impinges on it? And you're basically calculating the wave solution. Mee's theory is basically the solution for a sphere that's homogeneous, that has a different speed of light inside and outside, and may also absorb. And that's what Mies set out to do. And nowadays we have codes that could do a little more than that. They could do non-spherical particle, they could do coated sphere, they could even do, you can even build a very, very complex particle. But the more complex they are, the harder it is to get solutions. And because you need convergence, there's issues of conversion. Basically you write it as a series of some wave solution, and then you sum them up. That's the way it works. So what particles do we have in the ocean, and do they look anything like homogeneous spheres? No. They vary in size, they vary in shape, they vary in pigment composition, and therefore we expect them also, I mean, some of that will be also consistent with sphere, but we expect them to scatter and absorb differently depending on what they are. Here is a coccolithophore. These are calcium carbonate shells, with a lot of very different fine structures. You have here chains, like the chain we had in the lab yesterday from the diatom. You have things that are relatively spherical, a whole variety of particle. So those were the algae. Now we have non-algal particle as well. We have sand, silt, clays. Clays are little, thin plates. We have bacteria. Those also have some color. There's some pigment in them. Cytochromes, things like this. And we have these aggregates, this agglomeration of, some people call them marine snot, that you can see when you jump in the water, and Jesse loves them. Me too. So we talked about the size, so you should choose some sort of a size, and we talked about what the non-spherical, can you do it for non-spherical. Composition. So composition is characterized by the bulk index of refraction. So it's basically they're made of many different material, these cells. We talked about, they have organelles and things, and we're changing it in a sense to have one index of refraction that describes it. So it's a reduction. Instead of having many different organelles, each with its own little thing, and some people are trying to model that. This is with N1, this is N2, etc., etc. We come up with an approximate object. It could be the same shape or not, but it has a change of speed of light that's averaged over that particle, even though it might go fast and then slow and then fast again, or things of that nature. Okay, so, and there's a really nice paper I told you about by Haas 1996, where he builds a phytoplankton from its components. How do you get to an index of refraction of about 1.05 or 1.2 for something that's made of many different things? Oh, I jumped over several of the slides. So that would be a fun reading for you once, if you have time. Oh, I jumped a lot. Am I going backwards? Yeah, okay. Okay. Shape, so departure from sphere, micro, so you can have large departure, so you elongated versus thin, and you can have these micro things that we just saw for here. Things that are much smaller than light wavelength. So light, so this is about 2 micron. So these are probably 0.2 microns, so less than the visible light. These little, the internal structure, homogeneous within. We have a cytoplasm, chloroplast, vacuole, if you're diatom, and packing, how solid things are. So why may we care about optical theory and Meath solutions? So these solutions have been used a lot and have given us a lot of insight as how, despite the fact that they're for an idealized particle, we learned a lot from them. As I show you, geometric optics applies to many types of particles. It's used in the list as one of the possible inversion. You can also use a natural particle one. It's used to calibrate sensors, flow cytometers. We put beads in them because we know how beads scatter. Backscattering, you'll calibrate, you yourself will learn how to calibrate a backscattering sensor using precision beads, for which the Meath solution will give you what you should expect to have as the optical properties. In addition, for a given concentration of particle of a given size or wavelength ratio and index of refraction, we expect a given signal, which is very strong. We know what to expect. It's the one time you'll put, when you go and explore the ocean, you get a signal, you say, is it reasonable, is it not? I'm not completely sure, maybe I found a new type of waters. But when you put the bead in your instrument, you know exactly what you should expect because there's a physical solution that's exact. There's several people that came out of this class. Rebecca Green, who used Meath theory in their thesis. Rebecca Green used Meath theory to analyze flow cytometer data and be able to assign a size based on the forward and side scattering of that of beads in her flow cytometer. Joe Dalomo later on actually did it. He's a scientist now in England. Used Meath theory to analyze Dail cycle in optical properties, and Theo Kostadinov used Meath theory as part of his thesis to look at the effect of change of population size distribution on remote sensing reflectance. So you can argue whether it's the right theory to use, but people have used it and learned and used the codes that you're going to get to do exactly that. Some of the initial groundbreaking work on using this theory to analyze optical properties of particle was done by Morel and Bricot. Bricot just got the Yale Award this year. And it's really amazing work. What I did not realize, Anik in this paper from '86 was, as far as I know, the first to decompose an absorption spectra into Gaussian associated with each individual pigment. So she took an absorption spectra in the lab, just like you take, and broke it in. Many people have done it since, quite a few, including Ali Chase in my lab that you'll get to see. And broke it into Gaussian associated with individual pigment that you expect to have in that culture. And then it turns out there's a theory, an analytical theory called anomalous dispersion by Kettler-Helmholtz. I mean, these are probably two scientists that predict how absorption changes the real index of refraction. So this is the imaginary index of refraction derived from an absorption spectra. So you see, this is imaginary. So it's 4 pi. N prime is 4 pi times the absorption by the cellular material times the wavelength. So it's non-dimensional. This is one of the inputs into Meath theory. Yes?
I know you said absorption by cellular material, but that relates back to when we were talking about looking at the attenuation of light through a cell and the concentration within the cell and what its absorption was, which is separate from the bulk absorption that you guys are measuring, which is the medium with stuff with particles in it. This is actually just look at the attenuation through that cell. So it's a very high absorption. The value is very high relative to what you would measure.
It's as if you have a soup that was all cytoplasm, the whole cell material. Not in the water, not with water diluting it effectively.
And is that measured?
Well, you can infer it from your absorption measurement.
Okay.
You can infer it from your absorption measurement. We'll do an exercise like this later.
So you get an absorption spectrum that we're used
You get an absorption, and you can, if you know the concentration, you know their size distribution and how many you had, you can backtrack what they're likely, what's the best fit imaginary part of the index of refraction that fits your culture.
Right, from the
But you need to know how many you have in order to do your measurements. The details are in this paper. But using this theory, there is an effect on the real index of refraction due to the imaginary index of refraction. These oscillators, these Gaussian, have these, each one of them has a little variance on top. It's on the order of 0.005 for the biggest absorption peak. So it's not a lot on the real part of the index of refraction, but it's noticeable. Where do you see it? You all seen it in the, when you do the ACS-C beam attenuation, you see this little thing near the 676 absorption peak? That's this. That's this effect. Nobody has yet used it, as far as I know, to get chlorophyll out, but you should be able to use that little bump and this theory to back out what's the likely absorption that caused it. Should be a nice project one day. So basically what they've done is, for a known size distribution, known concentration of cell, being able to back out what the optical properties of cultures were. What's the real index of refraction, what the imaginary, and model this is the efficiency factor, so it's the beam attenuation cross-section. So again, it's beam attenuation of one particle divided by the geometric cross-section. So based on size, you know what the geometric cross-section. And they're getting results that are very consistent between model and measurements of scattering, of attenuation, by just inverting the absorption. And they have a backscattering here, but for this one they didn't have measurements. So it's only model. So you can build an optical model, this is what they've done, of a culture. And they've done it using me theory. So assuming that you can model a cell as an homogeneous sphere. And they got reasonable results when it was with respect to absorption, scattering, and attenuation. So this is just one aspect. Another aspect is, from these theories, and this goes back to an approximation by van der Hulst, we can collapse all these curves of beam attenuation to mass or volume that I talked about in the previous day if the x-axis is a non-dimensional number. Now, most people hate it, but engineers and physicists love it because it allows you to have all the complexity that's associated with change in size, change in index of refraction on one plot. So this plot as an axis has this phase shift parameter, n minus 1 times 2 x is pi d over lambda, pi d over lambda. Why pi? Because it's a sphere. There's always a pi where you involve a sphere. Diameter to wavelength ratio. So this is one thing that's important, but the other thing that's really important is this change of index of refraction, which tells you how phase legs are wave going through the particle, therefore slowing down, or accelerating if it's a bubble, compared to those that are passing outside, diffracting. So when you do that, suddenly everything falls on top of each other in terms of these resonance curves I told you about. The magnitude, of course, is higher for the more different you are from the water, the more you attenuate. The more you're like the water, as we saw when we put these quartz tubes in oil, the less you attenuate or scatter. And this allows us to also look at optical regimes, which are defined by these non-dimensional parameters. So we talked yesterday, we talked about the solution for Rayleigh, we talked about geometric optics. But I don't want to get this size. I want to talk about other things. So now I'm going to go to backscattering ratio. And many of you, for the homework yesterday, looked at this paper by Twardowski, where using me theory, we were able to get a phase space where backscattering ratio is here, and the slope of assuming a power law, it should not be say Young, it should say power law exponent here, we have lines of equal real part of the index of refraction. And then when we go and throw our measurements on top of them, they fit, just like they did for you. This is from 55,000 observation on New Jersey shelf, from places where we had resuspension of sand, all the way down to algae-dominated surface water, and in between them, which is amazing. Now, why is this amazing? Because I've been telling you that backscattering me theory doesn't work really well for backscattering. Yet I'm telling you, we've done it with me theory, because at the time we didn't know better, and we're getting something that's consistent with the data. This bothers me for years. I know me theory should not work, yet I'm getting something that my data fits on. Thank God that other people have decided they're going to do that study. So I'm going to show you in a second. It turns out coated sphere can fit both observation of backscattering and total scattering. And when they redid that same calculation, here it is. They redid the same calculation we did. They found that for the power law of 4, which we said is kind of the canonical value, the backscattering ratio increases by 58% for phytoplankton, now taking into account internal structure by having coated sphere. So instead of modeling it with a homogeneous sphere, now they say, okay, it's a coated sphere that we're going to use. And I'll show you some more results as to how we got into those models recently. And then for inorganic, only 12% change. If they do a coating, but there's no, most inorganic are solid. So these are the new curve where the solid ones are the ones consistent with this study, and the dashed line are the new result for. So overall, it's not a huge change, thank God. So this is why you can use this new curve and throw your data on. You're still going to be on top of them. Because the changes are about, instead of we saying it's an n 1.05, maybe it's an n of 1.04. The nice thing with this phase diagram is all our observation had only a factor of about 7 from 0.005 to 0.035 for everything we had in backscattering ratio. So this is sufficient to say organic dominated, inorganic dominated. And the uncertainties in our instruments are smaller than that change. So we can separate composition, we think. I'm not going to get into that. That's package effect. We already talked about it. Shape. Okay, any question about what we talked about, composition in terms of index of refraction? Yes?
Can you just give me some reason why new theory isn't supposed to work?
B theory in the back direction, because we're finding, so there's a long history in optical oceanography where everything from measurement from space to trying to look at measurements in the lab, backscattering predict by me theory is too low based on the particles we know. And so it was called the backscattering enigma. There's a paper, it's summarized nicely in a paper from 2004 by Stramsky. Where is this missing backscattering? It's called the missing backscattering enigma. And what some people thought it's submicron particles because we know they have a higher backscattering ratio than big particles. They thought there must be some small particle nobody has ever measured that are there. It's actually the topic of the thesis of Eric. I think he's looking for those missing backscattering with small particles. Other people said, no. If you look at observations of non-spherical particles, they backscatter more than those that are sphericals. Other people said if you just do concentric spheres, you do a cytoplasm and a cell wall, you're getting more backscatter. And I'll show you here result. So that's the reason why we're missing backscattering. So if backscattering cannot be modeled by me, what really is really disturbing is why is this working? What am I doing? Why is this working? This is me, the underlying lines are me-based.
But you said that it didn't change a lot for
Thank God, this just came out, 2018, December 2018. And they redid the calculation, and they're finding that there's no big change for backscattering ratio. For, again, under the assumption of the size distribution they used, etc. So,
But just
the model bias, there was a bias in the model, but the bias is not huge.
for only phytoplankton?
For phytoplankton, for the phytoplankton-like particle, the one they use for oligotrophic-like, you get for this size parameter, you're getting about a 58% increase. You still can very well differentiate it from inorganic dominated, which is the purpose of this exercise, is to try and say, am I dealing with phytoplankton suspension or am I dealing with sediments? Okay? So that was really, really cool when I saw it. Yeah. We used the wrong assumption, but we were not that far off. Yes?
Might be
But I mean, and these are all modeled. These still need to be validated. And I'll show you a validation of this kind of model really soon. Yes?
might be a loaded question, but is the backscatter enigma solved?
I'll show you a paper. I'll show a result about it. We can argue if that's the ultimate solution, but some people have. It's coming.
Okay.
Yes.
Using these lots of publications, that measure backscattering, you can actually go if you're really interested and go to these publications and try to put the odds in the plot and see how differs the observation and because they did it from all, so you just go through in your extra time if you have it. Go to the literature search, just go and try start putting dots there and see if the behavior of these papers actually is representative in that way.
So behaviors of shape. So here we're getting to shape. And the first question you may ask is, does it matter in the ocean? Are particle non-spherical? I showed you a lot of photos of non-spherical. But here is an analysis of a big data set from San Francisco Bay. It's the only one we could put our hands on, where people have looked at the axis ratio, the long axis versus short axis of phytoplankton. They reported it. So there's 8,000 measurement. And what you see, most of them tend to be like this in their data set, like this, as opposed to a plate. This will be, one of them is oblate. I think this is oblate, this is prolate, but correct me if I'm wrong. And this is a sphere. So this is the simplest model of shape that you can come up after a sphere. It's a spheroid. I mean, you can do also cylinder. It's also almost as, but this doesn't have sharp corners. So we like it, but you can use a sharp corner one. Anyways, so most of them look like this compared to like this. And it turns out that when you look at the least inversion, it is affected. If you use sediment or glass sphere as your reference, you're going to get, and both have passed through a sieve of the same size, they're going to get you slightly different peaks in the near forward direction in the VSF. Assuming, so for those that have the same cross-sectional area. So people have come up with ways to work for codes for non-spherical particle. A T-matrix does it really well. It can do also other shape. There's Chebyshev shape, all kind of weird, of different axis ratio. Unfortunately, they don't solve for all sizes yet. So there's holes when you're trying to do a size distribution. You cannot get a solution for everything. So these are prolate. These have axis rate. These are more plate-like. And oblates are more like this, so more like a football. This is an oblate spheroid. So that's the top there. Sorry. And if they're oriented, you're going to get very different scattering patterns around them compared to a sphere, because orientation matters. How much the light goes through, how does it resonate with the wavelength. Typically, we assume that, and we can derive solution for random orientation. And as long as the ocean is turbulent enough, that's probably not a bad assumption. But some people are questioning whether it works everywhere, whether there's place where particles are orienting, and it does affect your optical field. So here is an inversion that we've done in the lab. You remember this cell, the serratium? I told you what's the size it has? Well, if you run it through the list and you do the inversion of it, you're going to find 3 peaks for this culture. One peak that's associated with the size of this part, one peak that's associated with this part, and one peak that's associated with the whole of it. So that's what the inversion assuming spheres peaks out of your culture for something non-spherical. So it has a VSF that's affected, in a sense, by all the different size scales it has. And this is what you'll assume if you used an equivalent sphere that has the same volume, and this is what you'll get if you assume an equivalent sphere of the same area. This one, in terms of size. So you don't get that. You're getting as if you have 3 populations of different size particle in your mix. So shape matters. You could use it, and we've used it you actually can use the list to do a whole variety of things, including seeing how, as a culture grows, it changes and divide. Because that's in, and you can, that's enough for that. I want only to show you shape. So if you do the modeling of shape for these spheroids, you can do the modeling. You cannot fit for backscattering, you cannot do, so what I have here is aspect ratio. So this is, again, my prolates, oblates. I have the phase shift parameter, rho, and this side. Here it's particle diameter, assuming a red wavelength on the bottom. So you're more, it goes from 0.2 micron to 200 micron. An inorganic particle here, an organic particle, phytoplankton-like or inorganic-like here. And this is the ratio of B scattering by the non-spherical to the spherical of the same volume. So if it's more lighter, you get a large difference. Lower, you get a small difference, and this is your sphere. And it turns out, when you're very small, you scatter like a sphere of the same volume, so you don't have a big difference. This is the same data, just on a linear plot. But as you're getting to particle of about 0.5 micron here, you have a big jump because of these resonances we have initially. And then when you go to geometric optics at the big limit, you have much more scattering and more backscattering also for the non-spherical one, because they have more cross-section. The average cross-section, I told you, sphere has the minimal cross-section of every of objects that are I forgot the name. Simple objects that without holes in them. A sphere is the extreme. It has the least cross-sectional area, and because when you're large, what matters is cross-sectional area. If you compare to a sphere of the same volume, you're going to have more cross-section if you're non-sphere, and the more non-sphere, the more cross-section you're going to have, and therefore more effect on optics. And same goes, the same for backscattering. Now we go to internal structure, which I alluded to before with the backscattering ratio. But if you have internal structure, and initially you just assume a cell wall and a cytoplasm inside, what turns out is the near-forward scattering is impacted mostly simply by the size of the object. Or in this case, the cytoplasm is determining it. But if you have a thin wall around it, it determines the backscattering. This is what gives you the most contribution for backscattering and enhances it compared to just the inside cytoplasm. So this is the optical property of just a shell, and these are the optical properties of just a cytoplasm. And you add them up, you're getting the optical properties of a concentric shell, concentric particle in a sense. This is from a paper by Meyer from '79. So the backscattering is dominated by this membrane. And that's a recent study, again last year, Emmanuel Organelli took measurements, beam attenuation all along from England to the Falkland Islands. There's a cruise every year. And then took measurement of backscattering. And anything he tried to do with me couldn't put models and measured on the same line. If you use spheres of homogeneous sphere. However, if you use coded spheres, and he ended up with an index of refraction of 1.06 for the in and a one. I think it's 1.1 here for the out. Suddenly, he could match both of them for all his observation across track. Both backscattering matched the observation and beam attenuation matched the observation. And he ended up with, so this is 1.1, and he ended up with 1.18 as being the optimal one, and a cell wall about 5% of the total diameter. You were the reviewer of the paper, Ken.
I'm not. It was in oceanoptics, and it was great because look at, I mean, you're probably going to say, I was going to wait till you.
No, go for it.
Look which way it made things happen. It took the measured was always higher than the model, the upper right there. And it sort of brings that back to where they agree with each other. So we talked about the missing backscattering.
So this is, you asked, is there an answer for the missing backscattering? This is a paper that suggests an answer. And this is why it was in Nature, I think it's in Nature Communication, because I felt it's important enough that we need to yell on the,
Oceanoptics meeting, it was amazing. It was great.
yeah.
But he gave a great talk.
No, but I think you were a reviewer because he derived also the polarized properties. From these codes, you can derive polarized properties.
Forget papers I reviewed.
So this is back to the back. So remember this backscattering. You remember Colin showed a paper by Stramsky et al. From 2001 where they derived the properties of many different cultures. And some of them were based on me. Not the measured was the absorption, but the scattering and the backscattering were based on me. This is a paper with which you saw some data of already from Whitmire et al. This is cultures, a whole bunch of cultures. And what she finds is for all these cultures, significantly more backscattering than what was predicted by me theory in the paper by Stramsky. So significantly higher, not scattering. Scattering, they're on top of each other. But because scattering is mostly the cross-section. But backscattering significantly higher than what you'll expect if you assume they're homogeneous spheres. So this is the paper, again, that Kurt alluded to, where Craig Boren, an amazing physicist who studied light, wrote, so the name of the paper is Backscattering by Non-Spherical Particle, a Review of Methods and Suggested New Approaches. It's from 1992, I believe. And he said, even near forward direction, scattering by an arbitrary packet is not equivalent to that of a sphere with equal cross-sectional area. And that depends on, obviously, on size, another thing, Bourne and Co. Although the differences are not strikingly large. Near the backward direction, however, differences are much larger, as evidenced by figure 2. So as evidenced by just what I showed you here. Really large differences in backscattering compared to total scattering. This figure ought to be cause of concern for those who use me theory to predict backscattering or to invert backscattering measurements. However, when criticized for using me theory where its applicability is dubious, modelers sometimes responded, although they know that me theory is inadequate, it is the only game in town. Better to do wrong calculation than to do no calculation at all. Modelers have to model. We suggest an alternative to modeling. It's called not modeling. Not modeling, that is, until inadequate methods are at hand. It's beautiful. It's a JGR paper at a time when people could still provide opinions in papers, which is wonderful. You know, you could say what you think, and it's, you know, 92, if I'm not mistaken. Anyways, so remember this on everything you do. I mean, this is part of what I have on my back from a previous class. You can use it, you can help. It's a very useful tool to develop intuition, but make sure that you use it for what it might likely be applicable. And know its limitation everywhere, whatever model you use. So here is a study. This is from a study that's completely different. So we're done now with me. Now I'm going into still staying with shape. study done by Howard Gordon, and then there were several following studies to try and understand the complex optical properties of this very important species called Emiliania axlei. It's important for a variety of reasons, but one of which is we can grow it in the lab. So literature is always biased to things we can grow in the lab versus what we can't. Just so you're also aware of that. The species we know the most about are those we can grow, those we know the least about, even though biogeochemically they might also be very important, we don't hear about. But these are really important in oceanography for us because they color the ocean. When they have a big bloom of this, you can see it from space very nicely. Yes? And a lot of sediment, the Dover Cliff, you go to Jerusalem, it's all, I mean, not just this species, but a bunch of species of that nature that are calcium, that precipitate calcium carbonate. They make shells.
And they're responsible for a ton of carbon export.
So, significant species. And a thing that Howard wanted to know is, does it matter to light a lot, these little structures? Does it change a lot the optical properties of this thing? So he did a bunch of calculation. And also, when the leaf detached, these get released by the organism. You can also detach them when you grow them in the lab and see their effect on scattering. Does it matter, how does the optical properties of everything detached compare to the whole? And overall, he found that the goal study was to obtain some understanding of the differences between the backscattering of a collection of such objects, like this, in random orientation, versus homogeneous disk of the same size. In this regime, the backscattering is they're small, totally governed by the particle gross morphology and the effective index of refraction, meaning that these serration were not strongly affecting you could model them with something like this without taking into account these little lines. But modeling something like this is not trivial. I think they used a dipole approximation, the discrete dipole approximation, where you basically build this thing with dipoles. But you could do it. It's possible to do it, just very, very labor intensive. So now I'm moving to aggregation. This is the last topic I'm going to talk about. So aggregation is this thing where particles stick together, and because they stick together, they become effectively larger and they sink faster than their component particle in the ocean. The marine's not. It's a concentration square phenomenon, meaning if you double the concentration, this is going to go 4 times faster because you have more particle opportunities to run into each other. Mechanism for encounter could be Brownian motion. It's usually in the ocean not important, so that's just movement because water molecules jitter with temperature. Differential settling, meaning a fast particle captures a small particle as it goes down, or a slow particle. And turbulent shear, meaning water movement brings particles together, they bump into each other. They sink faster than the component particles, so it matters for export. And they break when shear is too high. So usually the limiting size is not bigger than a centimeter, and this is really cool. And it's intuition I got from Paul Hill, who's going to come here next week. As they fall, shear is formed, and then they'll break. So that limits how big they're going to grow. Yes, Juliana.
I have a question about the yeast and the Brownian motion and the graph you showed with the slope and the no, it's just not.
So Brownian motion happens on very small scales, and for for a small particle. So it does not particles that are micron size are not affected significantly by Brownian motion. It will bring together tiny particles.
So the Brownian motion.
And I think this is, by the way, Einstein Nobel Prize, I think, was on Brownian motion, the one he actually got, and not on the rest of the stuff he did. Yes, just an aside.
If it's so very small, okay, then maybe. So the Brownian motion assumes it's random distributed. The particles are random, right? Distributed. Like they encounter and then they run to the other side. Like they keep moving and it's randomly.
Yes.
Okay.
And turbulence, in a sense, is doing a similar thing. There's eddies are bringing particles together, and at a small scale, these eddies are 3-dimensional.
Okay. So assuming you have particles that have like different axes, so they have a small and a large one.
Yeah.
These encounters are going to make my particles.
It's likely to change the probability of encounter.
Okay, so that might be
No, I don't think so.
No, because at some point it could be, looks like it's spherical or something like this, or maybe.
No, I mean this is an important process, particularly where you have a lot of stuff in the water. Not when so it's not the order one effect that's going to affect what you're observing. I mean, I don't fully understand your question.
But I think I'm familiar well too. But Brownian motion also happens. The chances of encounter with for waters pouring particles. Am I familiar, right? So Brownian motion also happens when you have pore waters, like moving.
Oh yeah, in the sediments, yeah.
Sure. So when you're measuring it and these particles are moving, I know I introduced like a bias over uncertainty because I'm going to be measuring these particles like many times.
Oh, so you're asking if when we handle water, do we affect it? Yes.
Yeah, but so
We affect the size distribution. So if you're in a place where aggregates are important and you're taking water and then measuring it in a Coulter counter or even in a list by pouring it, you're changing the size distribution. So some of my colleagues, they don't believe any size distribution measured on land. And what they do is they do the disaggregated size distribution. They on purpose breaks aggregate before they do size distribution because they don't want to, then they know their bias, but they know they've done something to it so that all are biased similarly, as opposed to this one was shaped more, this one was shaped less, and it changed the size distribution. So yes, size distribution do change due to it. But these aggregates are large. And remember, when we looked at the slope of the beam attenuation is mostly focused on particles smaller than 20 micron. But in the least, it will affect you strongly, as I told you. If I run my pump and break the aggregates, I'm going to measure a different size distribution in the water.
But if I have like silt, it's not going to break.
What?
If I have silt, okay, I have high silt, like they're flat instead of the cylindrical.
Silt.
Yeah. So
Yeah.
like if I'm measuring them, I'm going to be measuring the same particle in many different shapes.
Orientation.
Yeah.
Yes. Yeah, and shapes. Yes.
So-
And those are actually quite strongly bound to each other when they're in salt water. Yes. Yeah. Yeah.
But so this, if I measure the same particle, let's say twice, the bigger axis and this,
Yeah, so it's true for any individual particle, but if you're assuming they're randomly oriented in the water because there's sufficient turbulence in the water, these are the result I showed you before, is for random orientation. Then maybe an inversion like the natural particle for the least would work better than a spherical one. So one way to test for sensitivity to that is to run your inversion on the list with several type of inversion. The natural particle one, the mean one, and if they differ a lot, you have a large uncertainty in what you expect. If they're mostly similar, then probably you have more certainty in what you're trying to say from that inversion.
Is that not what we were talking about with widening the particle size?
Yes, it would likely, any non-sphericity will widen your size distribution because you see it in this orientation, in this orientation, in every possible, as we talked yesterday. You'll see me this way, you'll see me this way, you'll see me just from here. And so you'll have a wide size distribution as a result.
based on this, I can calculate BB, right? Based on the measurement from the least.
No.
Can I get?
Well, you can put it into a model that calculates BB.
Okay, yes.
Yeah.
And then,
It doesn't mean that BB is correct.
yeah, but I'm trying to think about the Young's relationship. Do you think this works from?
But one of them was based on a size distribution, power law, and assuming it's a power law for all the sizes. And the other was measured backscattering over total scattering, which is not what the sensor measured. There's a new list VSF which measures both. Yeah.
I was talking about the block strength.
So you're talking about the phase function. Now, so you're talking about the ratio of the forward to back in this. How will this change as I change shape? This to this.
No, I was talking like the plot we plotted for the presentation this morning. The one.
The backscattering ratio to the one where here I have.
Yes.
Okay, so here you have and here you have BBP over BP. And you're asking how will changes in shape affect these results.
What I'm talking is like if the Brownian motion distributes the particles randomly and this multiple measurements of the same particle in different
Orientation, yeah.
could that make it, the particles as like an average of the beams look like a spherical instead of elongated in axis?
So this I get from size distribution. So I just, one parameter. And I only if it fits correctly. So I get a size distribution, I fit this. The shape could move things between sides. I don't know if for natural population, I don't think it's going to change this parameter much. This changes a factor of 6 between inorganic and phytoplankton-like. BBP will increase with non-spheristic. BP will also increase. I have more cross-sectional area, maybe less than BBP, but maybe by 30%. It's going to be a small change relative to this. It will add to the uncertainty of the inversion, no doubt, but I don't think it's going to be a significant departure. At least, as I told you, when we throw data from the field on this diagram, we're getting reasonable position. Where we expect the organic, we see the organic. It's natural particle with all their crazy shapes and everything. When we expect the inorganic, we find the inorganic. And again, it's all bulk. Don't forget that when we do measurements, we have it all in one big soup. Does this answer a question? Or we can talk about it afterwards. So when I go with sedimentologists to the water, what we're finding is that you can have very big changes within a day between when aggregates are broken, you have strong shear in the water, to when aggregates are formed. This is when you have less turbulence, because in large, and they can be really large. These are order centimeter, or maybe a few hundreds of millimeters. Yeah, these are bigger than a centimeter. Okay, and this is 12 meter in a. So, how do you model an aggregate? You go to the literature, and you find a paper by Latimer, and he tells you, well, an aggregate it's not a very bad assumption for an aggregate. You don't see it well to assume a non-spherical particle and a shell. And you take these two models and divide them by 2. And he compared it to lab measurements of aggregates of all kind of stuff, and it worked reasonably well for A, B, and C, not for backscattering. So we've done that, and when we do that, and we assume a certain pore size, pore material, amount of water, what you find is that this resonant interaction moved to bigger and bigger and bigger particle. The more water you have in it, the more you get interaction with bigger particle. Such that beam attenuation to volume stays constant. You don't get this resonance you're going to get for one culture. Because you have a lot of aggregation, beam attenuation to volume or to mass stays relatively constant over all sizes, which again might explain why Heel, when he reviewed the literature, found these to be relatively insensitive to places around the world. Again, this is the observed range for aggregates. This is beam attenuation over mass, diameter of particle. For all particle, almost, we have very small, narrow range, which is in the range observed in the field for CP to mass that people do. While if I did it with assuming single grain, assuming the aggregates are big single grain over all sizes, I would have lost all this mass that because of accepts an angle. So the water fraction is based on a paper where they tell you the bigger it is, the more water there is in it. So aggregation approximately conserve area and not volume. This is not just accept an angle, I'm sorry. What this is the fact that you have you have less surface area to volume as you go to a big particle. And basically aggregate conserved cross-sectional area, because the parts that makes the aggregate are not shading each other. In a large aggregate that's full of water, you can get interaction with almost everything in the light interact with every particle in there. And so people describe it with fractal dimension, and as long as the fractal dimension is above 2, meaning it's still, you cannot see through it, this is the interaction you're going to expect. If you become a see-through, it's more like a sum of the individual particles that are in it. Okay. So we did this in the lab to see if indeed, so this was theoretical. And then in the lab, what we did an aggregation experiment where we took something like your Arizona dust, we put it in. We have all our instruments on the bottom of this big tub. And then we're adding some salt to make them form aggregates. And you look at what happens as function of time. So what happens in function of time, initially you have the SPM is constant, the same amount of material in the water, and then it starts settling below our instrument, we lose it. Size distribution based on the list. Initially they're not aggregating, they're aggregating, and then you're getting from a particle about 4 micron to 2 micron of this small, you're going up to 30 on average of your aggregates of clay. And then when you look at beta, we have one of the VSF meters you've seen, a beam attenuation of the list, a beam attenuation of the AC9. They all are about constant, and then they start going down as we lose particle. Everything up till now you expect. But if you look at optical properties divided by mass, they almost don't change throughout the whole experiment. So as I'm forming aggregate, they're opaque, they're full of water enough that I'm not getting this self-shading within my big, large particle. So I'm not losing the cross-section, the optical cross-section that you lose. If they form a dense particle, you would have lost it. This would have gone down really much. The only thing you lose is acceptance angle effects that you particularly see. And they're not very big. It's about 20, maybe 20% that you see in the first and mostly in the AC9. Sorry, the AC9. Interestingly enough, and this we did not predict because we could not do the theory for. Same happened with backscattering. As the aggregate formed, we did not lose backscattering for the large aggregate compared to the small one. And for this, we had no theory. Yes. Well, what I mean by shading is that if I have a material, a big particle, very soon after light gets in and absorbed, the material that's behind it does not interact with light. And if I divide by mass, which I do here, this is all mass, but this is all mass that did not interact with light. If I'm small, close to the wavelength of light, maybe all the material has interacted with the light. But when I'm big, only part of it. So as I divide by mass, I expect things to decrease like 1 over diameter, it turns out, because it's a cross-section that matters. If you're dense.
So for the aggregates, it's like spread.
They're spread sufficiently, exactly. The material in the aggregate is spread such that I'm not losing the Think about a cotton ball. Think about a cotton ball as you spread it. Usually I bring a cotton ball to class when I talk about it. So it's the same amount of material, but taking much more volume, such that everything can interact with the light. And you're not losing. So aggregation does not kill you in the field in terms of ability to predict how much mass I have. Yes?
So over the course of this experiment, as things are aggregating more, there's more material being added to the...
No, you're losing material. You see, you're losing material. Total SPM goes down because stuff settles. As it aggregates, it sinks faster, and we lose it. Yes?
Adding salt.
We added salt just in the beginning, mixed, and the salt is what caused them that when they touch each other, they would cling to each other. Yes? And this is an effect that is not like aggregation in the ocean. This is completely artificial. You guys should do these experiments with cultures. You guys should do experiments just to affirm that indeed with natural materials you can get the same. This is completely artificial, except for the fact that we form aggregates. Whether these aggregates behave like aggregate in the ocean in terms of light, I hope. But it confirmed the theory that we derived before it. But if you guys want to grow cultures, mix them with sediment, see what aggregates you form. Try by stirring them really fast in the beginning, start with small particles, see them grow and fall through the instruments. You'll find something nobody did. I'm sure. Anyways. So, Yes. Oh, sorry.
Well, maybe it's a stupid question.
The note is stupid question.
So your mass specific stays the same, but aren't you losing mass because you have the
You are.
attributes are set?
But you're also losing light. You're also losing material interacting with light. If you're losing concentration of particle, you're also losing, there's less of them to interact with light, so your signal goes down. So both mass and signal go down, but the ratio stays relatively constant.
What did you call them the other day? There's,
Intensive and extensive
exactly.
properties. And this is a, mass specific is an intensive property. It doesn't depend on concentration. So if I lose concentration, I'm still okay. Ostetler always talk about it. So again, for aggregate, we cannot assume that we can use just me theory to model them. And aggregation is essential for predicting underwater light fields and settling velocities. So this is really matter, particularly people that work in coastal, but also in the open ocean with respect to. I showed you this one. If this was done at the dock, we can break aggregates in the ocean. You can do it yourself again. You can take an instrument, break the particle before they go in, and see if it makes a difference for your measurement. And if it does, that tells you that these aggregates can matter. This is me in the Bahamas with my CTD and AC9 on my back. In short, there's still a lot of work in ocean optics, and we count on you guys to do it. You have to account for diversities in shape, diversity in internal structure, diversity in packing, and both theoretical and observational advances are needed. Polarization might help you. More volume scattering function measurements. We have very few, as you heard. All these things are going to make you change the field. Anyways, thank you. Unless you have questions. No questions. Awesome. So how much break? 15 minutes? 20 minutes? What? 15 minutes? And then... And if you have questions, come to me. I mean, we can talk about it now and we can look at... Riley, can you close it?